Ever notice how your phone's camera sometimes misses your smile when you're wearing a mask? Or why AI struggles to tell if someone's angry or just tired when their face is half hidden? That's the tricky world of facial expression recognition, or FER. Today, we're diving into a breakthrough study that's rethinking how AI handles occlusion, the sneaky problem where parts of a face get blocked. Let's break it down. FER is all about teaching computers to read human emotions from facial cues. But here's the catch: real life isn't perfect. Sunglasses, hands, or a bad angle can hide key features. Traditional AI models, they get confused. Think of it like trying to solve a puzzle with half the pieces missing. The researchers behind this study noticed two big issues. First, existing models lack semantic understanding. They don't grasp the big picture of facial features. If a face is partially covered, they might focus on the wrong areas, like a nose instead of a smile. Second, most datasets have way too few examples of occluded faces. It's like training a dog to recognize cats, but only showing it pictures of dogs. So how did they fix this? Meet ORSANet, a smart new system that's like giving AI a pair of superpowered glasses. Here's the magic. 1. Semantic maps. Imagine a detailed mask highlighting every part of the face: eyes, mouth, cheeks. These maps guide the AI to focus on the right areas, even when parts are hidden. 2. Facial landmarks. Think of these as tiny GPS points on the face. They help the AI understand the face's structure, filtering out distractions like skin tone or gender biases. But how do these pieces work together? The team created a multi-scale cross-interaction module, a tool that combines different levels of detail, from broad shapes to tiny textures. It's like having a microscope and a telescope in one device. Plus, they designed a special loss function called DARELoss, which dynamically adjusts how the AI learns from tricky cases, making it better at telling similar expressions apart. To test their ideas, they built a brand new dataset called Occlu-FER, the first of its kind. It's packed with real-world occlusion scenarios, think masks, hands, and shadows. And the results? ORSANet smashed the competition, achieving state-of-the-art performance. This isn't just about better AI, it's about creating systems that understand humans more deeply. Whether it's improving virtual assistants, enhancing security, or even aiding psychological research, ORSANet is paving the way for a future where technology sees the world as we do: messy, complex, and full of hidden stories. Ever wonder how your phone can recognize your smile, or how security systems might detect emotions? Behind the scenes, researchers are pushing the boundaries of facial expression recognition, a field that's transforming how machines see human emotions. Let's break down some of the latest breakthroughs that are making this possible. At the heart of this work is a simple yet powerful idea: teaching computers to interpret facial cues with the same nuance humans do. But here's the catch: human faces are complex. Subtle changes in a brow, a twitch of the lips, or even lighting conditions can throw off a machine. That's where these studies come in. Here's the really cool part: these models aren't just getting better at recognizing emotions, they're becoming more robust in messy, real-world scenarios. Take MMATrans, a 2024 framework that focuses on muscle movements in the face. Think of it like teaching a computer to spot the difference between a surprised gasp and a fearful flinch by zooming in on the tiny details of your facial muscles. Then there's FER-Former, which adds a clever twist. It doesn't just look at a face, it pays attention to the whole scene. Is someone slumped in a chair? Are they standing in a crowded room? These clues help the model guess emotions more accurately, like solving a puzzle with extra pieces. And it's not just about faces. Researchers are teaching AI to handle tricky situations, like occlusions, think masks or hats, tricky lighting, or even cultural differences in how people express emotions. One study used noise-tolerant learning to train models to ignore irrelevant variations, making them more reliable across diverse scenarios. The future of FER isn't just about seeing faces, it's about understanding the full story behind them.